Okay, so QuESTlink. What have we seen? We've seen Quest, which is this C or C++ hardware accelerated simulator. We've seen PyQuest, a Python interface to that. Now let's look at QuESTlink, a Mathematica interface to that. No, to the underlying Quest, but that would be hilarious. So what is QuESTlink? Well, it brings the power of Quest to Mathematica. Mathematica is Stephen Wolfram's brainchild, a symbolic computational system, which is emerging as like the de facto tool among scientists and physicists, or at least in my circles. If you haven't played with Mathematica, you really should. It's really cool. I'm going to show you some of that soon. Why does it exist? Well, here is some Quest code. This is real code. You can run this. You get a number out. But you can see, I mean, the boilerplate's not too bad. It's not the ugliest C code, but it's very wordy. There's a lot of characters on the screen. Why did we spend so much time making Quest hardware accelerated and GPU accelerated and multi-threaded? The point is to shrink one quantity, which is time, and I guess computing resources if you pay for your supercomputer. We want to get the answer to you as the user as fast as possible. Why? Why does that matter, that your code runs as fast as possible? Oh, well, you're waiting for the result, right? So that turns into your time. But if we really wanted the code to be as fast as possible, why don't we just write everything in assembly? Just write your paper study of the Hadamard gate in assembly. Well, obviously, development time is part of the metric to optimize. It could take us a year to write something in assembly, which then maybe runs in a microseconds, or it could take me 4 minutes to write it in Python, and it runs in 1 second. So your time as a user needs to be part of the ultimate metric which we're optimizing by making things faster. If we give you a simulator that's really fast, but your development time goes up proportionately, you haven't actually saved any time. In fact, you're probably just wasting energy, because it's better to use your brain's energy in coding than to use your HPC center's energy budget on cooling GPUs that are doing nothing. So this is this is Quest code in C, and Richard, using the same logic I just described, has presented to you PyQuest. So PyQuest abstracts away a lot of the nuisances of dealing with C and C++. So this is a step in that direction, optimizing the total time, that is runtime and your time. But I'll do you one better. No. If you've used Mathematica, then you'll know that Mathematica is very, very quick to develop if you're doing certain things. Things that we formulate naturally in mathematical terms are often just as easy to instantiate in Mathematica code, whereas they can be very difficult to put into Python or C code. So this same code snippet does essentially the same thing. I changed a few gates. But what's really special about that bottom right code, which is some Mathematica code using QuESTlink, is that this is the installer. These 2 lines of code at the top give you QuESTlink. They give you Quest, and they give you this Mathematica abstraction layer above it. So if you have Mathematica, you can be running that right now, installation free. If you're coming to the parallel session 1A on the capabilities of QuESTlink, we'll go through Mathematica generically, and then we'll talk about QuESTlink. Okay. I definitely didn't write these speakers' notes in the back of the audience. Okay, let me now bespeak the extreme ease of using Mathematica by live coding, and definitely not because I didn't have time to prepare this presentation. So I'm going to switch now to a Mathematica Notebook Live, which means I need this screen to stop being a secondary screen and instead become a duplication of my full screen. Great. So here's how you obtain Quest. You use the inbuilt import statement, how you obtain QuESTlink, pardon me. qtech3.org/QuESTlink. So this command, qtech3.org/QuESTlink.m. This is it. Now, you're going to see a warning here. One thing that's nice about this model of development is that I can push changes straight to your machine. So when I discover a catastrophic bug in a function, such as reported here, I can let you know as a user instantly. The very next time you run QuESTlink, I can say, whoa there, I patched this function. For the record, this is the first time this has ever happened. But let's just quiet that with the quiet command. Okay, so now we have QuESTlink. Yeah, that was hard. We have all these functions available to us in addition to the Mathematica inbuilt symbols. Quite a lot here. The first thing I want to do is I want to rerun that circuit we just saw on screen. So I'm going to create a quantum register. Actually, I'll create a density matrix. Oh, wait. Getting my wires crossed. We've obtained half of QuESTlink. The functions you just saw are symbolic front-end functions, which I'll explain what that means later. But we want the meat of Quest, which is the high-performance numerical backend. To get that, we need to download a precompiled executable of Quest. Now, if you wish to use hardware acceleration, like your machine's GPU or multi-threading, actually no, multi-threading we include, then you'll need to do a separate step, which I won't show now. If you just want to get the thing loaded, you're happy with a relatively slow numerical simulator, you can run this command, create downloaded QuestEnv. What this does is check what operating system you have, check if we have a compatible binary pre-installed, which lives on our GitHub server, so nothing dodgy, it's not going to our private server. If you have a compatible OS, downloads it, and now you have QuESTlink. So now, it might be hard to notice in this format, but now there's a lot more functions available here. Yes, you can measure it by how long I'm scrolling for pointlessly. So, let's use this backend. I'm going to create a density matrix. Here is our 7-qubit density matrix. Actually, I'm going to want to look at this state, so I'm going to make it a little smaller. Make it 3 qubits. Let's specify a circuit. We use a syntax which is very natural to the quantum information theorist. We use the same subscript syntax you'll see in papers. So here's an X gate applied to the first qubit. Or here's a controlled Y gate, controlled on the first, acting on the 0th. Some more boring gate. Yell out your favorite gate. What's your favorite quantum operator? Hadamard. The Hadamard? Jesus, this guy sucks. This guy's boring. What else? The Toffoli. Oh, well, I can do that in swaps, right? Is that double controlled X? I'm barely a theorist. Let's do some rotations. So I'm going to rotate around the x-axis by 0.1. Maybe I'll do a control on the first 2 qubits to rotate the z on the last qubit. Whatever. Depolarizing. Damn it, I only have homogeneous depolarizing. Here's homogeneous depolarizing, 2 qubits, that's pretty special. If I want 2 qubit inhomogeneous, I need to make my own Krauss map, which I can do. However, producing a Krauss map live in front of an audience, I will not be doing. Okay, so here's my circuit so far. I'll just evaluate that. If I look at it, it's just a Mathematica list, nothing special, so I could do lots of modifications to it if I want. I could, for instance, append to it a final S gate. Why not? How do I apply it to the state? Well, what is this state? You can imagine if this was a matrix of complex numbers, like you might expect a density matrix to be, that would be pretty damn inefficient. That would mean that I'm storing that matrix in the Mathematica front end. We don't want to do that. If only Quest needs to move the numbers, just let Quest keep track of it. So this is actually just a pointer, the ID 1, to a persistent quantum register that's being stored exclusively in the Quest process. So there's no duplication. Richard mentioned that memory movement is really like the metric we wish to optimize against. Don't move memory superfluously. This is in that philosophy. So to apply my circuit, I apply the circuit in this way. Done. What we got back there is an empty list. That's just because had the circuit contained measurements, this would contain our measurement results, which would be pseudo-random. What did that do to the state? Let's find out. I hope it did something. We started in the 0 state. Let's see if the probability of the first qubit being in the 0 state has changed. Ah, my poem. Yay, it's not 0 or 0.5. Okay, there's the probability of the first qubit being in 0. Well, we had some noise here. We had some depolarizing noise. A probability 40%. That's pretty severe. What did that do to the purity of our state? How mixed is it? Oh, it's pretty bad. This should be 1 if it was a pure state, but now it's 0.49. So you see, like we're doing these calculations. This isn't Mathematica. These calculations are happening in the underlying C process, or C++, whatever, and the results are being returned to Mathematica. What's cool about that is I can then use local hardware efficiently. If I had set up a server which I bloody should have done, but I swear I've done it before, I did it live in Texas, I could be connecting to a hardware accelerated machine, like the GPU in my office, and be dispatching all the instructions you just saw with the same code to that GPU, and have the results sent back to me completely seamlessly. So all this code would be identical, or this code would be a little different. It would have an IP address. And I would get the same numbers, but it would come back much faster with a little latency overhead. So that's what's really, really nice about the separation between Mathematica and QuESTlink. Yeah. OK, now before I'm going to speak now no more about QuESTlink's numerical features. Now I'm going to get really into what's special about it, like what's the difference between this and hooking up some other simulator to Mathematica. And before I do that, are there any questions about this so far? Is everyone on board with what I have just done? Yeah? Oh, sorry. We have no time for questions. So documentation, there will be documentation for QuESTlink coming soon. There is currently no standard library for producing Mathematica-style documentation. So if you search for a Mathematica function, in fact, I can do something like this, right? This opens up this little standard thing. There isn't like a Wolfram official way to do this yet. So QuESTlink still doesn't have that style documentation. Instead, somewhat as a nuisance, you have to query the full API with this command. This is that weird little tilde key that nobody uses. And then I can just click a function like apply circuit, and it will give me information about what it does. Or if I know in advance the function I want, I can do question mark, sample classical shadows, and it will give me some information. But documentation is on the to-do list forever. It's perpetually in my backlog. Any other questions before I get to the juicy stuff?
Are you going to show the circuit visualization? In which case?
No, I was thinking of excluding that. So yes, so that's part of the things that the power of Mathematica will bring to Quest. But OK, so if everyone's happy with the numerical side, let's get into the graphical side. Why might you use Mathematica in the first place? Because it makes things quick and easy, and it has lots of excellent visualization facilities. So let's look at the circuit that we just simulated. Here it is. Here's the circuit diagram. If you're a Mathematica guru, then you won't be surprised to learn that this is just a big expression. There's one giant plain text expression. So you can modify things programmatically very easy. For instance, I want to replace the RZ with, let's do something appropriate. I don't know, hi. There it is. I replace RZ with hi. I want to replace every key. Oh, let me not get overboard. Anyway, well, that's cool. What else can it do? We can calculate the analytic matrix associated with this circuit, which is pretty big because it's, oh, it's only 2 to the 3. Oh, how many qubits are I? 3. Did I leave something symbolic? Oh, here it is. Oh, it's my zoom. OK, yeah, here's the matrix. All right, yeah, fair enough. That's the Z-basis matrix that describes this operator. You might notice it's more than 2 to the 3 big. That's because this is actually a super operator matrix because my circuit contains this decoherence channel here. So I'm going to remove that for the sake of visualization. And now if we plot it, I've removed that and the escape. Whoops. And now I get this lovely 8 by 8 matrix. OK, that's useful if you wanted to check, is the analytics of my matrix correct? But notice it's all full of floating point numbers. Ooh, I thought we were avoiding those. Well, that's because we had floating point parameters in our circuit. Let's go ahead and change the Rx parameter to a symbol, theta. Oh, yeah, let's change the RZ to phi. Is that phi? Now, nothing's changed in the circuit. If we plot it again, everything's the same. But our matrix is now symbolic. Woo! I can now do a bunch of analytic symbolic calculations and only later substitute parameters. That's one of just many, many functions to analytically or symbolically study circuits. What else can we do? We can draw the circuit topology. You know, I want to say, oh, is there a gate acting between these qubits? Yes, there was, because it's all to all. What else can we do? If you like Pauli transfer matrices, we can draw those now. Which will be this. Now, this might be very expensive because the Pauli transfer matrix is 4 to the 3 in size here. Yeah, we better not. Oh, it's big. Well, there you go. You can draw it if you want to. Let's just do one operator of that, hey. Oops. Yeah, you got it. Yeah. There you go. There's the very boring. No, we can do cooler than that. Are you kidding me? Okay, here's the Pauli transfer matrix associated with 1 qubit damping noise. So you see that there's lots of graphical ways to study circuits. I neglected to mention before that we can actually get the entire matrix describing our quantum register out if we wanted. So here is the density matrix of our state rho after we applied that channel. This is something worth avoiding. As Richard mentioned with the QuEST interface, you really want to avoid moving lots of memory around. If this was like a 25 qubit density matrix, oh, that would be too big. If it was a 15 qubit density matrix, this would be a 2 to the 15 by 2 to the 15 matrix. Way too big, you'll crash your kernel, or you'll get really slow code if you try to run this. So in lieu of running commands like that, we use all the nice existing functions in the QuESTlink API, which include... Is any of this interesting? Let's see. Okay, let's implement an algorithm. Woo! What's your favorite algorithm? Give me your favorite quantum algorithm. Trotterization? Thank God you said that. Okay, let's first get Hamiltonian. So trotterization, if you don't know, is a method of performing real-time simulation of the dynamics of a system described by a Hamiltonian. So we know the real-time dynamics analytically are described by the Schrödinger equation. If our evolution is unitary, then it would be described by something that looks like this, exponential, matrix exponential, of our Hamiltonian h, whatever. This is a big operator. If h is like, 5 qubit system, this is a 2 to the 5 times 2 to the 5 operator. So in trotterization, we instead produce a quantum circuit which approximates the action of this evolution operator. So let's first start with a Hamiltonian. Hamiltonians are just as easy and concise to write in QuESTlink as they are in the literature. Here's my Hamiltonian. I get 0.1 of x, so Pauli on the first state. Here's 0.4 of x on the first, the 0th, x on the 1, y on 2, z3, etc., etc. You get the idea. Okay, there's a Hamiltonian. We can do lots of things to study that. For instance, we can get the matrix associated with it. I'm going to use this function. Here is the dense Z-basis matrix that represents this Pauli string. Now you see why we use Pauli strings, because they're so sparse. Let's say, in fact, let's make these coefficients analytic even. In fact, let's make this a goddamn expression. We have to use a different function for this. Oops, should hit enter. Here is now the analytic Z-basis matrix of this Pauli string. Whoa, symbols. What good is that? Well, I can't remember the functions.
Can you take a derivative, for example?
Yes. So one thing we could also do, so we could use the power of Mathematica for that directly. So, here, this is a, what do we call it? A first-class Mathematica citizen. So this is just a real Mathematica array. That's symbolic. So yeah, I can compute the derivative of m with respect to the parameter g. Here it is analytically. G was defined, it wrapped in this f, so whatever this f symbol is, it's got its derivative here. So I can pass this to like any existing Mathematica function, such as matrix plot, did I imagine that? Yeah, etc. However, if you're simulating, say, variational quantum algorithms where derivatives of quantum operators appear a lot, this will be too slow for systems at scale. So we actually have functions for polynomially accelerated calculation of derivatives of quantum operators, which I think is called calc_deriv. Apply circuit derivs? What does this thing do? Yeah, we've got some functions for that. We have functions, for instance, to calculate the metric tensor, which appears in variational algorithms such as natural gradient, and, quantum imaginary time evolution, etc. Okay, but back to Trotter. This is a pretty uninteresting Hamiltonian, so let's just create a random Hamiltonian. I think there is a function, yeah, get random Pauli string. Let's use that to create a random Pauli string. We'll do 4 qubits, 10 terms, coefficients between 0 and 1. Hey. Yeah, and there it is. There's our random Pauli string. Now, I could write the Trotter circuit myself here, which would be fun, but I can use an existing implementation of circuits. So this function, getKnownCircuit in QuESTlink, is a convenience function that has a few canonical circuits used in the literature for you to just invoke, so you don't have to write your own generators. This list will grow, and also there are like secret parameters for some of these, so you can give a list of qubits out of order here, whatever. We want the Trotter circuit. So we say Trotter, we give it the Hamiltonian. Now, Trotterization has an order hyperparameter, which the higher the order, the more accurate your simulation, but the more computationally expensive it is in terms of quantum resources. Let's do order 1. Repetitions is another tunable hyperparameter. It's just the number of times to repeat your circuit. Let's make it 2. And we'll keep the time that we're simulating to symbolic, because I'm too lazy to pick an answer. Here it is. Here's our Trotter circuit. Let's draw this. Beautiful. Yay. We could even calculate its matrix. Which is going to be 2 to the 4 by 2 to the 4. I'm too lazy to evaluate that. So we could, let's replace t with a number, which we could do afterwards like this using Mathematica syntax, e.g. But let's just whack it in to time 1. Oh yeah, Richard?
Is this any different from there's a Quest backend function that does Trotterization, but it doesn't return the circuit, right? Is that different?
Yeah, so this is completely decoupled from that. So I don't know if I even did Trotter. Right, so that function is not exposed in QuESTlink. So Rich is just pointing out, if your ultimate goal is to affect the Trotter circuit, you don't actually need to do this circuit preparation. There are functions in Quest, and I assume in PyQuest, that apply the Trotter circuit for you. And sometimes in an optimized way, i.e. merging gates into each other for a more efficient simulation than a circuit decomposition. But let's just say maybe I'm going to mess with the Trotter circuit or something. So here's my Trotter circuit. Well, let's apply it to our state. Is this on too many qubits? This is on too many qubits. So I'm going to create a new quantum register. Okay, I'm going to create a quantum register in the plus state. How am I doing on time? I'm going to apply that circuit to it, our Trotter circuit. Oh. Let's see what I did wrong. Derivs, get that out of here. Okay, it's applied, and now I can look at the state I produced, should I want to do that. Okay, there's your Trotter circuit. What would be more interesting if I plotted the accuracy of that or something? What could we vary here? Okay, here's what we'll do. I've got 8 minutes before Ash gets up. What I can do, take our circuit U, and let's insert some noise. I'm going to make, okay. I'm going to make as many depolarizing operators as I have gates on a random qubit between 0 and, how many qubits we got? 4? The index is from 0, so we've got 4. And it's going to be an amount that we set. I don't want to do it. Okay, I'll just do it like that, whatever. Oh, nice, that worked really well. Doesn't seem so random to me. What the hell happened here? We've got 4 because I indexed from 0, so the highest index is 3. I guess this is evaluating once. That's so annoying. Oh, you're right. You've actually done it. There we go. So now we're going to riffle this into U. So now what I've created, let's call it D for depolarizing channel. I've created this circuit. You see, after every operator, we now have depolarizing noise. Is that sufficiently realistic? I don't know. Then what we could do let's create a new state. We'll also put it in the plus state now. Let's leave it 0 state. A noisy quantum state, i.e. a QReg, still 4 qubits. We can just check that this circuit applies. We have a symbol X. Let's make it a small number. OK, great. So what I'm going to do in 5 minutes, we're going to put our density matrix back to the 0 state. Then we're going to apply the state where we have changed the noise parameter x to g, where g is going to be something I vary between runs. Let's go between 0 and 0.5 in steps of 0.01. That's fair enough. So I'm going to apply the circuit, my trotter circuit. Oh, I need the true state. That's annoying. All right, we're going to do something really lame. I'm just going to gather the fidelity of the state. Oh, that's what we want to see. This is a density state. A density. Really? If you see an obvious mistake, I'm making a point down. Oh, fidelity, right. Sorry. What I want is the purity. Yeah, that's pretty lame. All right, well, here's our data. Let's line. Okay, what I've done here is I have repeatedly applied. What? Show me all. I have repeatedly applied the trotter circuit, increasing the noise severity after each gate. So I'm increasing the noise severity of all of these, rerunning the full trotter circuit, and then looking at the resulting purity. So unsurprisingly, when you increase depolarizing noise, your purity falls off. Not as exciting as if I showed you the fidelity with respect to a true state, but then we'd have to get the true state, which could I? Oh, I could do it in 4 minutes. Okay. We have the Hamiltonian. That's our Hamiltonian as a matrix. Let's instantiate the unitary time evolution operator. It looks like an imaginary number, the Hamiltonian, and then the time we're simulating to, which I think I had set to 1. Right? Yeah, right there. Okay, we're going to simulate the time 1. This is our evolution operator. What we need to do is get the initial state. So it's a 0 state of 3 qubits. Let's just do it ourselves. It's the first state of, is it 3 qubits? 4 qubits? I feel the time pressure. Is it? Wow, what a stupid argument order. Okay, we're going to apply that. Here's our output state. Now what I'm going to do, I could just do the inner product myself in Mathematica, but I want to do something slightly cooler. I'm going to create a new state. 4 qubits. I'm going to set its register to be out. So see, yay. What I'm doing here is, what's that?
Does that make it a density QReg?
Yeah, so well, I've made a new QReg, and now I've set it to this 4 qubit state. So now I can do calc fidelity between rho and psi. Whoa, 0.06. So now what I'm going to do, rerun this. And here it is. It's a slightly different curved line. But this is now the fidelity between the real trotter state, so the real evolution state, and the approximate trotter state.
Can you show the visualization of the density matrix? I don't think we've seen that.
Sure. Here is, experimentalists like this, apparently. Here is our density matrix. I mean, it's almost a fully mixed state. Why don't I really quick, let's just set the maximum fidelity to the maximum probability to 0.5 in steps of 0.01. What I've just done is modify this state. There you go. There's a pretty density matrix. Okay, I hope that convinces you to give QuESTlink a try. If you come to the session this afternoon, which is 1A, we'll see more of this. And you can throw me an algorithm and I'll try to implement it into Mathematica. Okay, thanks very much.